There is a machine operating in the lignite mines of Germany that weighs more than 14,000 metric tons and stretches 220 meters in length. It moves continuously, day and night, week after week, without ever fully stopping. Not because the operators forgot to turn it off, not because stopping it is inconvenient, but because stopping it incorrectly could destroy it. That is not an exaggeration. A bucket wheel excavator brought to an uncontrolled halt under the wrong conditions can sink into the ground under its own weight. It can buckle its own conveyor structure, or create a load imbalance so severe that the entire machine shifts on its crawler tracks. The engineering that keeps it running is inseparable from the engineering that keeps it from destroying itself the moment it stops. Most people, when they imagine shutting down a large machine, picture a sequence of switches and levers, reducing power, disengaging systems, parking. The mental model comes from cars, generators, construction equipment, machines that can be stopped at any point in their operation cycle without consequence. That model does not apply here. The bucket wheel excavator is not a machine that happens to be large. It is a machine whose size creates operational constraints that have no equivalent in any other land vehicle ever built. To understand why stopping is so complex, we need to understand what the machine is actually doing at every moment it operates. The Bagger 293, the largest bucket wheel excavator ever built, has an operating weight of 14,200 metric tons. Its bucket wheel alone is 21.6 meters in diameter and carries 18 individual buckets, each with a capacity of approximately 6.6 cubic meters. The wheel rotates continuously, each bucket scooping material from the mine face as it passes. It deposits material onto an internal conveyor that runs the length of the 200-meter boom arm. This material transfers to a second conveyor on the counterweight boom, and finally to an external conveyor system. This system carries the excavated material away from the machine entirely, ensuring the massive operation never grinds to a halt. At full operation, the Bagger 293 removes up to 240,000 cubic meters of overburden per day. That is not an intermittent process. The wheel rotates, the buckets fill, the conveyors move, and material flows continuously from the mine face to the external system. Every component in this chain is dependent on every other component operating at the correct speed and capacity simultaneously. This continuous flow is the first reason the machine cannot simply be turned off. The conveyor system carries thousands of tons of material. If the bucket wheel stops suddenly while the conveyors continue, the conveyors empty but the excavation stops. Manageable. If the conveyors stop while the bucket wheel continues, material piles up at the transfer points within seconds, jamming the structure. It jams under loads it was not designed to absorb as static weight. If everything stops simultaneously, the material remains on the conveyors. This is a distributed static load across a structure designed for dynamic loading, and the machine must be manually unloaded before any restart. The sequence of shutdown follows a strict protocol. The bucket wheel stops first, ending excavation. The conveyors continue running until they have cleared all material from the system. Only then can the conveyor drives be brought down. The process takes time measured in minutes, not seconds, and cannot be safely compressed. The ground beneath the machine is the second constraint. A bucket wheel excavator does not operate on prepared concrete or stable bedrock. It operates in an open pit mine, on ground that has been partially excavated and may be saturated with groundwater. The crawler track system on a machine like the Bagger 293 consists of 12 individual crawler units, each a self-contained drive system. The total track contact area distributes the weight across a ground pressure of approximately 1.7 to 2.0 kilograms per square centimeter. This pressure management depends on the machine being in motion or correctly positioned. When it stops on specific ground. If the water table has risen or a blast has disturbed the compaction, the tracks begin to sink progressively. A machine that was stable when it stopped can become partially embedded within hours. Repositioning requires the drive system to operate under extreme load. In the worst cases, external assistance is needed. This is why the Bagger 293 must keep moving to stay alive. This is why bucket wheel excavators do not park in one place for extended periods. When operation pauses, the machine is positioned on firm ground. Extended stationary periods on marginal ground require preparation, compaction, drainage, and sometimes the laying of steel mats to distribute the massive load. The machine's weight does not change when it stops. However, the ground's ability to support that weight over time definitely does. The third constraint is structural. The bucket wheel excavator is not a rigid structure. It is a complex, dynamically balanced system. The boom arm extends up to 100 meters, while the counterweight boom extends opposite. The entire structure rotates on a large slewing ring bearing. During operation, loads are dynamic. The wheel generates cyclic forces as each bucket engages the mine face, while conveyors create constant vibration. The structure handles these loads within specific parameters, but when the machine stops, dynamic loads disappear, leaving only static dead weight. A boom angle balanced during operation may create an uneven static load distribution when stopped, potentially stressing the structural frame. Conveyor belt tension that was appropriate during running may become excessive or insufficient once the drive system is unpowered. The slewing ring bearing is particularly sensitive. These massive bearings are designed for rotation under load, not for prolonged static pressure. Static loading can cause local deformation of bearing races, called brinelling. This creates permanent damage that affects rotation smoothness. Long-term stationary periods require periodic small slewing movements to distribute the static load across different sections of the bearing race. The electrical system adds another layer of complexity. These machines run on grid electricity, typically at 6,000 to 30,000 volts. The motors driving the bucket wheel and conveyors are large AC drives, some producing thousands of kilowatts individually. Managing these systems during a shutdown is essential to ensure the longevity and safety of these incredible feats of engineering. These drive systems do not shut down instantaneously. They ramp down through controlled deceleration sequences managed by the drive electronics. An uncontrolled power loss, a grid failure, a cable fault, or a protection relay trip forces emergency shutdown procedures. These procedures are fundamentally different from planned shutdowns. Emergency systems apply regenerative braking to the drive motors. They use the kinetic energy of the rotating systems to generate electricity that is fed back into the grid or dissipated through braking resistors. This controlled energy dissipation is what prevents the mechanical shock of an uncontrolled stop from damaging the drivetrain components. Even with regenerative braking, an emergency shutdown from full operating speed produces mechanical stresses throughout the drivetrain. The bucket wheel drive, large synchronous motors driving through a multi-stage gearbox, decelerates the wheel and its 18 loaded buckets. The torques involved during this deceleration are among the highest the drivetrain will ever experience. This is why the drivetrain components are inspected more carefully after emergency stops than after planned shutdowns. The emergency stop works, but it is not without cost. The crawler drive system presents its own shutdown considerations. Moving a 14,000-ton machine requires all 12 crawler units to operate in precise coordination, the same speed, direction, and force output. If any crawler unit fails, the others must bring the machine to a controlled stop without inducing lateral forces that could cause skewing. A machine this size moving slightly off-path can place the boom arm over ground that has not been assessed for the load. Repositioning after an unplanned stop requires a full survey of the machine's actual position relative to its planned path. This includes assessment of ground conditions and a controlled restart sequence that verifies all systems before resuming excavation. This process can take hours. In a mining operation, an unplanned multi-hour stop has measurable consequences for the mine's output. The maintenance shutdown, a planned stop for inspection and component replacement, is the most controlled version of this process. Before a maintenance shutdown, the ground is prepared. The sequence is followed to clear conveyors and balance the structural loads. The crawler units are positioned on the firmest available ground. The boom is lowered to minimize static bending on the slewing ring. The electrical system is isolated in sequence, with each drive system ramped down in the correct order. During the maintenance period, the machine is not simply left standing. Ground condition monitoring continues. The slewing ring is periodically moved. Belt tensions are checked and adjusted for static conditions. The bucket wheel is locked in a position that balances its load on the drive shaft. When the maintenance is complete and restart is planned, the ground is reassessed. The systems are brought up in reverse sequence, and the machine transitions back to operational status. Through a controlled startup that verifies each system before imposing load on the next. The bucket wheel excavator operates at the intersection of several extreme engineering domains simultaneously: structural engineering, geotechnical engineering, electrical engineering, and mechanical engineering. And the constraints from each domain interact. A decision made in one domain ripples through the rest. The ground condition affects where the machine can stop. Where it stops affects the structural load distribution. The structural load distribution affects the bearing condition. The bearing condition affects the startup sequence. The startup sequence affects the electrical system ramp-up. Every element is connected. So why can't a bucket wheel excavator simply be turned off? Because the machine's mass, its structural configuration, its ground interaction, and its material flow system are in managed equilibrium. And that equilibrium does not simply pause when power is removed. It must be carefully transitioned to a stable static condition through a controlled sequence that accounts for every load path, every ground condition, and every system dependency simultaneously. The machine does not stop the way a car stops, or the way a conveyor belt stops, or the way any machine whose size does not fundamentally change its physics stops. It transitions from one managed state to another, and managing that transition correctly every time is as much a part of operating the machine as managing the excavation itself. If you're thinking about what happens when one of the crawler units on a machine like this fails during operation, how the remaining units respond, how the machine is brought to a stop with asymmetric drive, and what the recovery looks like. That sequence of events connects directly to everything discussed here, and I've covered it in another video.